Our other speaker is Ganesh. Since 2003, Maya has worked at the intersection of media, digital technologies, advocacy, and human rights as a researcher, writer, and information activist. She spent 8 years working on this with Tactical Technology Collective, which is based in Berlin and works to develop kind of tactical strategies for the use of technology, not only here in the West, but in the global South as well. She has 2 master's degrees in applied psychology and in media and cultural studies, and she's currently a doctoral candidate in Leuphana University, investigating machine learning and accountability, and she has a wonderful capacity to traverse the worlds of both practice and conception and thinking about the future of how we'll use technologies.
Okay, so I actually don't have very many slides. I'm just going to keep this one on, and I have 2 slides that come right at the end. So I don't really need that. So thank you for inviting me to be here. Thanks to the CCA, the Goethe-Institut, and the Speculative Life Cluster at Concordia, especially Orit and Chris, who are old friends. So in late 2017, there isn't yet a fully autonomous car, but there are significant efforts towards developing one. I'd like to talk about the displacement of the human through the scaling up of cybernetic thinking and infrastructure, the evolution of the car as a computational object, and the introduction of mathematics and measures to enable an environment for artificial intelligences to govern themselves. I call this math, model, and flow. It might also be called autocorrect. My work is about the evolution of autonomous driving, and I'm interested in real and imagined crashes in particular, as a place from which to study this evolution of standards and measures through mathematics. And I argue that discourses of ethics and accountability that you hear a lot in the press around autonomous driving are part of that process. Putting an autonomous vehicle on the road is not a new enterprise. In fact, since the 1950s, engineers and city planners have been trying to come up with ways to erase the human, which is considered to be a hindrance in the fusion of car and road. In 1956, the magazine Life profiled the new highways administrator at the time, Bertram D. Talamy, saying of him as an engineer that, quote, he can visualize technological developments that will necessitate new forms of highways and introduce new concepts. One of these, he thinks, just might be a system of traffic and vehicular controls whereby the motorist can relinquish the wheel and his car speeds along in perfect automatic safety, end quote. In 1960, Norman Bell Geddes, the great reimaginer of cities, asked how driving may be remodeled. He predicted that the faults of humans as drivers could be corrected by devices. Quote, everything will be designed by engineering, not by legislation, not in a piecemeal fashion, but as a complete job. The two, the car and the road, are both essential to the realization of automatic safety, end quote. Automatic safety, then, it seems, is the ambition of the vehicle. Yet in Cotton Sealer's Cultural History of Automobility in America, driving has been explicitly and implicitly shaped as a highly regulated activity, even while offering the illusion of freedom and escape via the freeway and the highway, your classic Deleuzean control society. So perhaps we are seeing the evolution of the car as more than just a computational object. Perhaps we're seeing the evolution of the autonomous car as the perfect neoliberal object that tootles along, making decisions for itself. The unruly body of the human is the thing to eventually control if automobility is to achieve its ambition. In a personal interview, an engineer at the University of Michigan's Transport Research Institute tells me that computers know themselves and can apply themselves 100% to whatever is asked of them. In an accident, for example, if a human has to hit the brakes, they usually do so only up to 80% with only up to 80% of the force required, and usually too late. Software responds at 100% and immediately whenever asked. Humans do not. But there is this consistent, constant back and forth and exchange and borrowing of metaphor and practice from human to machine. The makers of software for autonomous driving, the company Drive.ai, say, quote, we're building the brain of driverless cars, end quote. In a mirror image of what John von Neumann said over 50 years ago, the human brain is prima facie digital. We're in the hands-off stage of autonomous driving. We are not yet at the brain-off stage, quote, says the chairman of BMW. So we have the language of deep neural networks as well, in which we see the assumption made about how the human brain processes information. And the history of AI, artificial intelligence, is littered with such examples of language and ideas and frameworks borrowed and applied from one context to describe and understand the other. I feel like sometimes the human keeps wanting to project onto and merge with the machine, but perhaps machines and humans are just different. Madeline Elish and Tim Huang show the history of aviation autopilot as one of praise the machine and punish the human. Despite the increasing automation in the cockpit and possible design and engineering flaws which are responsible for accidents, responsibility still gets assigned to the human for crashes and accidents. The same engineer at the University of Michigan shares an observation. When a plane lands in difficult weather conditions like torrential rain, flooding, snow, and ice, people clap, believing that the pilot has done a superlative job. However, in such conditions, says the engineer, it is highly unlikely that a human is at the controls. The computer is. There's another case he talks about, quite recently, in fact, in the news, where a plane was supposed to go from Los Angeles to Minneapolis, but went an hour ahead of where it was supposed to go because nobody was paying attention because it was on autopilot mode. They had to turn the plane back when they realized that they were running out of fuel. The plane will just go until you tell it to do something else. So autopilot is a very interesting feature and one that I like to think of as a boundary object that's viewed differently by whoever is doing the viewing, and it is divisive in this sense. It was this nature of autopilot that came up sharply in the case of a crash involving a Tesla car in May 2016. A Tesla enthusiast and ex-Navy SEAL, Joshua Brown, was killed when he was test driving a Tesla in Florida when the image recognition software in the autonomous vehicle, in the Tesla vehicle, mistook the bright white side of a long refrigerated semi-trailer truck for the sky and slammed into it. He was killed, but the truck driver escaped unharmed. It is said that the car was in autopilot mode. If autopilot was at fault, then the car would have to be recalled and Tesla would be in trouble. But according to Tesla, the car repeatedly gave, or rather autopilot, repeatedly gave Brown warnings that he was to take control of the car back, but he did not. I've also recently discovered a whole stash of YouTube videos of and by Brown, who is a huge Tesla enthusiast, where he's constantly trying to trick and test the machine. He was expressly told by Tesla, however, not to. There's some recent updates on this in terms of new forensic testing that's happening, and I don't know how these YouTube videos are going to weigh in on this, but that's another story. So how must machines and humans do this handover? The handshake is messy. Engineers say that level 4 autonomy, or complete autonomous driving, is considered far safer because computers can be trusted to just be themselves. Level 3, which is like the Brown case and which we have now, in which human and machine need to interact, is messy. Doing an independent reading of Google's crash and safety reports from its driverless car project, scholars Brandon Shettle and Michael Zivak find that there were many small-scale crashes that the Google car got into that wouldn't be reported if they involved humans, just really simple rear-ending or bumps that, where nobody gets hurt and nothing major happens. They found that driverless cars tended to be rear-ended by humans. The cars follow rules, but humans do not. And scholars predict that a mix of conventional and autonomous or semi-autonomous driving is likely to see many more crashes. This crash avoidance has become the bread and butter of software companies from California to Tel Aviv. Getting machines to learn how to distinguish a soft living object like a cat or a child, and this is not my language, this is engineering language, from a permanent hard object or a temporary hard object is a challenge that is worth a lot of money and bandwidth. How this happens is training machines to repeatedly look at images of objects, break them down into pixels as a way to understand them, and then put them back together again to make sense of what that object is. Every time you fill in one of those visual captures online to prove that you are not a robot, you are effectively training computers to see and identify things in the world. Questions of accountability and responsibility in traffic safety have been outsourced to mathematics for some time now. The scholar Paul Lenardi describes the co-evolutionary processes of technological, regulatory, and organizational change in automotive engineering, particularly crash testing. He finds that there's been a shift in mathematics-based simulations and models as a way to cut costs in crash testing technologies. He cites Nigel Gale as first identifying the road to lab to math path as an industry-wide belief that mathematics is more cost efficient than road and laboratory testing. Lenardi goes on to show that mathematicization has been made to seem inevitable through a particular rhetoric around safety, risk, and crashes. He cites an executive at one US automaker saying, quote, "Road to lab to math is basically the idea that you want to be as advanced on the evolutionary scale of engineering as possible. Math is the next logical step in the process over testing on the road and in the lab. Math is much more cost effective because you don't have to build pre-production vehicles and then waste them. We've got to get out in front of the technology so it doesn't leave us behind. We have to live and breathe math. When we do that, we can pass the savings on to the consumer," end quote. But how do you set up measures and standards for safe driving? What is safe driving by an autonomous car? What is driving even? In the US, an individual may drive anywhere from 5 to 13,000 miles a year, depending on where they live. A driverless car does about 1 million in test situations and in simulations. That's more than a lifetime. How do we know what these measures actually mean and amount to? Is there a number that corresponds to when we know that the machine has done enough test driving to be safe? We need these new metrics and standards, but then how do we calibrate and establish these metrics and standards and what they mean? For example, if you say that you need 500 miles for a car to be tested and safe, then how do we determine which part of those 500 miles actually contribute to safety and adequate learning? It could be that 450 miles driven on an open, empty highway, which is fairly easy for autonomous vehicles, may not contribute to any substantive machine learning about safety, but the most important 50 miles done in a highly complex environment, like let's say Lower Manhattan, may be the most important. How many different scenarios do we need to establish and measure safety? There are also all these new languages of metrics being developed for how machines perceive, process, and analyze the world around them. For example, there's the time to reflect reality, in quotes, which is the lag time between the world as it is and the world as it is known to machines. This is the lag between sensors actually mapping the environment through radar and LIDAR and processing it within the limits of bandwidth and big data infrastructure. Perhaps the most compelling set of measures and standards being developed is decision-making about how to avoid accidents, which is being termed as the ethics of autonomous driving and something that is quite central to my work at the moment. Alan Turing wanted to know if machines can think, but as computer scientist Edgar Dijkstra put it, it's pointless asking if a machine can think as asking if a submarine can swim. So instead of machines that think, we are now at a place where we ask, how do machines learn? What is the Turing test for the present moment? Machine learning is the computational process by which self-driving cars make decisions about how to perceive, assess, and then avoid objects on the road and thereby accidents. So driverless cars need to be fed a lot of data about different kinds of objects and how they appear for machine learning to identify and recognize whether they should be sacrificed or not in a potential accident. So classical ethics tests like the trolley problem are being used as standards for machine learning, are being used as models for machine learning to make decisions about how to respond in potential crash situations. But this classic test sets up an irreconcilable problem. The trolley problem wants to resolve consequentialist with utilitarian ethics. Consequentialist from deontological ethics. Should the car, if brakes fail, hit 5 people or hit 1? The process of reasoning whether it should hit 5 or 1 is deontological, but saying that 5 people are more valuable than 1 is utilitarian. How would a machine know if the one person was the scientist who would come up with the cure for cancer and the 5 are an ISIS sleeper cell? MIT's Moral Machine project is an online research exercise based on the trolley problem, which you should go home and find on Google and play. They will take you through 13 scenarios in which you're presented in each of these scenarios with the car brakes failing. And in front of the car are a motley crew of society, for want of a better word, because you have to make a decision about should you hit a thief running away, or cute cats, or a pregnant woman, or just like a regular straight couple, a regular gay couple, It's just amusing to kind of go through this process itself. Of course, you are contributing to a crowdsourced model that they will eventually at some point feed into some machine learning process. But the trolley problem is flawed for many reasons I won't go into here mathematically and ethically. So other scholars have come up with other ethics tests to work as models, such as the Pascalian wager, which actually comes from the 1600s and Blaise Pascal. So in the Pascalian wager, calculations are used to rank different outcomes of crashes to arrive at an objective choice, because the people working on this believe that a view from nowhere is really important. However, we know from the humanities and social sciences that all knowledge is situated. There is no view from nowhere, however. So the cases of cars with failed brakes ramming into a child, an animal, a helmet-wearing cyclist, or destroying itself to save others are all given numerical rankings and coded. An algebraic calculation processes these rankings to arrive at the most mathematically objective outcome. The last of these models, the most recent, there's many of them, but one that just caught my eye recently was from Mobileye. They've come up, Mobileye makes the computer vision software that's used in Teslas. After the Tesla crash that I talked about, Mobileye and Tesla split, and Mobileye has now been acquired by Intel. I think Gretchen was saying this before, that keeping up with the business history and what's happening with the changing business patterns is also really interesting and something of a challenge sometimes. So Mobileye has come up with something called RSS, or Responsibility Sensitive Safety. The model consists of an extensive set of mathematical equations based on a comprehensive set of driving scenarios. So again, we go back to this scenario and its history to train machines. So Mobileye's Vice President of Technology, Shalev Schwartz, calls it cautious command. Any command that falls outside of these constraints would be rejected. RSS doesn't define the type of algorithms that should be used or the overall software architecture strategy for any automated driving system. It would be a more final sanity check, in quotes, before issuing commands to the actuators. Like Mobileye's RSS, it is possible that data currently being harvested about driver behavior from a variety of sources, highway cameras, police records, social media, insurance records, automotive engineering simulations, and so on, will be used to develop machine learning algorithms that will learn how to make decisions across different situations. Rezepka and Araki identify such an approach to enable what they call machine ethics. Quote, "It might be safer to have machines imitating millions, not a few, believing that such democracy-dependent algorithms allow the most people to behave ethically without actually learning ethics. They suggest searching the web for opinions, usual behaviors, common consequences, and exceptions by counting ethically relevant neighboring words and phrases, aligning these along a continuum from positive to negative behaviors, and subjecting this information to statistical analysis. They suggest that this analysis, in turn, would be helpful in the development of a sort of majority rule ethics useful in guiding the behavior of autonomous systems." Bonnie Nardi and Hamid Ekbia refer to this as heteromation, as opposed to automation or augmentation. Heteromation, in which the machine calls to the human for help. The world of gaming and gamification have already applied this to a great extent, from citizen science projects like folding of genomes to making decisions about dealing with abuse on gaming platforms. Crowdsource human behavior to develop a data set and to parse appropriate and likely outcomes in a mathematically legible process, to put it simply. Thus, we see that ethics is being shaped as a computational output and as decision-making by machine learning. We see a shift of ethics, from ethics as something that is based on logical reasoning to something that is based on statistical significance and the normal distribution. Therefore, embedded in a driverless car, self-regulating artificial intelligence that runs on machine learning that can distinguish objects in order to avoid accidents presents an idealized picture of machine autonomy. Such an approach limits ethics as a framework of values, and as Deborah Johnson says, accrues power to software itself rather than humans, or the contexts of software production and use. Mathematics-based modeling and design, then, for decision-making to avoid accidents has become integrated into what I'm calling infrastructures for accountability. Ethics is transformed from a framework of values and relationships into mathematics-based accountability. Gregor Chamayou, in talking about drones, actually refers to this as necroethics, as in like an ethics of who you can kill. We're building an environment for the car to be able to communicate with the cloud and other non-human intelligences to interface with a little help from human intelligence. The thing is, that driving is really complex and full of ambiguities, and yet we have to reduce this to models that can capture and anticipate complexity and ambiguity. Or perhaps what we're doing is we're changing what we actually mean by driving and automobility into something that exists entirely only between car and road. So I want to end with something that shifts the focus from cars and mathematics to an ethnographic encounter from last year. And in fact, something that Orit and Chris were part of. So this is a sketch I made of a visit to an automated car factory. What we found when we went to the car factory was that the car itself receded into the background, and what emerged was a demonstration of scaled-up cybernetic thinking, resulting in a factory that's shaped by logistics, which, as Zela and Rossiter put it, is the organizational paradigm of cybernetics. So in the smart car factory, as in the smart factory making cars, not the smart car factory, the loops and flows of information supersede everything else, making the fact of mediation, the design, the objects, and the people disappear. The flow is the thing. The design and architecture respond to and shape this notion of flow. In building the factory, architects measured the number of steps that one team took to speak with another team and designed their office in response to this. They wanted to facilitate synchronous face-to-face conversation rather than let them rely on email for communication, which is asynchronous. Everyone who worked in the factory, whether on the line or in the management office, entered and exited through the same set of doors. Office spaces had the assembly line passing through and across them. You could be having a face-to-face meeting or conversation with your coworker and find that a doorless car body was gliding past you on purple light-lit gantries above your head. Unfortunately, I do not have any photographs of this because we were not allowed to take any digital recording devices in, only rely on our digits to record things. 8 hours of taking notes was a once-in-a-lifetime experience. Most interestingly, the traditional notion of the assembly line itself as something linear was disrupted by these ideas of flow. So thus, the entire process of production was not a straight line anymore, as the assembly line is imagined to be, but it was bent into a triangle. The design of the factory, however, is the crown jewel. So in order to ensure that the process of manufacturing is never limited by the physical material limitations of architecture or the supply of raw materials, the building itself is designed, in theory, to expand endlessly. This is done by building the factory as expandable fingers rather than a square or limited building. So you have these fingers that keep extending out, and you could keep adding processes of automation and assembly onto them. These instances of cybernetic thinking in the design and process of car manufacture promise a sort of orderliness that is a counterpoint to the very disruption that the autonomous car is supposed to stimulate. Eventually smooth and flowing, cars and factories become infrastructural nodes, become data, become software. And I want to end with this little video that was actually made for Audi. And I think it kind of strangely echoes where the imaginings of Belgedis and Talami, where we have an automated environment for automated vehicles and software and grids to talk to each other without humans. of course, that's a whole other paper just on the aesthetics of and the visuality of our autonomous future of car and road. So thank you and goodbye, humans.